I'm Christine. For those of you who don't know, I'm a staff member in the Data Services and Workflows group at ALCF. So this is like a very hodgepodge talk, and actually it's going to kind of ask more questions than provide answers. So hopefully you guys can give me feedback. So wait, what are we doing? Okay, here we go. All right, so this is Parsl Fest. So and I'm from ALCF. How do we use Parsl on our machines? Well, I mean, some of it we use Parsl directly. Some of it we have users using it through Globus Compute or Globus Flows. We have our main production machine right now is a machine called Polaris, which is about 500 nodes with NVIDIA A100s. We have a new machine that's brand new, Aurora, which is the second exascale machine in the United States or the world, as far as we know, and that has about 10,000 nodes using Intel GPUs. So this is the context in which we're using these tools. There's a few different areas in where we're using them. So, you know, and you've heard maybe a bit about some of this, maybe at this meeting or previous meetings. One is computing for experimental facilities. That's using Globus Compute and Globus Flows. You know, we're working a lot with light sources. We have a light source at Argonne, the APS, where we've been doing a lot of work with them, but we've also been doing work with tokamaks and neutrino experiments. You heard from my colleague, Michael, about some of the work he's been doing with OpenCosmo, and that's in the area of computing services and sort of data portals. But we have other projects as well, Aurora GPT, which is our goal of creating a GPT-like service for scientists. But also, I think Tyler talked about, from OLCF, talked about some efforts combining both OLCF and ALCF resources to do work for the Earth Science Grid Federation, which is ESGF. And then we have kind of our more traditional work, you know, doing high throughput computing workloads. You know, a lot of this involves coupling AI, ML to simulations. You know, we have tools like Clumina developed by Logan Ward, who many people in this room know, and that leverages Parsl. So, you know, our goal at ALCF is just to make sure, help our users with tools like Parsl to efficiently run on our machines. So as part of those efforts, there's a few things we've done this year to try and help facilitate that. One thing I wanted to highlight is we contributed to the Parsl code base for the high throughput executor, a new method for pinning threads to workers that allows you to do an explicit pinning rather than using a strategy like block or alternating, which is a round robin. So now you can set a list of thread, you know, ranges or lists for each worker. And, you know, this is important for some hardware. For example, on Aurora, the number of CPU hardware threads is not evenly divisible by the number of GPUs on a node. So you kind of need to be able to skip some threads or assign sort of different ranges. So this is like a messy example you might use for Aurora, but now you have this ability to do this. If you've ever run MPI applications, this might look familiar to you. It's very much inspired. I see some nods, very much inspired by that, which is, you know, what we at a capability computing facility know. So that's what we did and what we contributed. Another thing we contributed is some improvements or just making it a bit nicer for launching multiple workers on an NVIDIA GPU. So, you know, NVIDIA provides a number of ways of partitioning A100s or H100s. This case was sort of motivated by their multi-process service. So now what you can do is you can oversubscribe essentially workers to GPUs. And Parsl, like before, this was possible, but it was very messy. You had to provide a long list of strings. Now you can just say, you know, a Polaris node has 4 A100s. If you want to spin up 8 threads per A100, 32 workers per node, you can just set available accelerators 32. And then in your worker init here, you need some, we provide in our documentation some scripts that will start the NPS service on the hardware. So you can just do this. It's a lot nicer. And I'll say this is the YAML format of configs that's used for compute endpoints. So that old way was very messy for this kind of format. And so now it's a bit simpler. Okay, I've got 2 minutes. So, okay, I'll skip this, but if people have thoughts, I'm just wondering if this is a problem. Challenges for large workflows. And so this is something that came up recently from one of our users. They created a Parsl workflow that created 300,000 tasks. And the resulting Parsl process that was running on one of our login nodes, sending jobs to the scheduler, consumed over 8 gigabytes of memory, which we will kill on our login nodes. So this is due to the memory footprint of the outstanding futures. So when the Parsl workflow creates tasks, it creates these futures. And as long as they're outstanding, they're contained within memory and they have some memory footprint. So, you know, this can be a problem if you're thinking about large workflows. And we have this huge exascale machine now. So if you just want to sort of think through, what are the number of workers you would spin up on Aurora for a high throughput workflow in our capability computing model? I mean, a minimum would be about 24,000 workers. A maximum would be like 500,000. You know, what is the memory footprint of a Parsl process with this at this like scale? Have we profiled the memory footprint of the Parsl processes? There might be many solutions, and some of them might be, you know, things we at the facility have to provide, such as hardware that has more available memory. But it does seem to me like maybe we shouldn't be having such memory-intensive processes that contain your entire workflow. I mean, running this way, and you know, I think right now power users kind of get around this by sort of throttling their task creation within their workflows. Like I've seen 2 different solutions for this now. What should we be doing? This is my question. If people have thoughts or experiences, let me know. So thank you.